7.9. And 7.10, I said because it's require a lot of complex things that we haven't learned, or we haven't learned. I will just mention the main point. I mean, like in my old video, I actually wrote it. Mostly, if you want all the details, look at my old video that posted on campus also. But just, but but the physics is important. I mean, the physical concept is for your knowledge is mostly uh, just for your background knowledge. So I'll just mention the physics of these sections of it. And it's based on the fact that we are talking about a complex this dielectric constant. The, uh, epsilon is a function of frequency. That's what we are starting point. The now it depends on spatial location, but it depends on omega. And then for a given omega, there's epsilon and multiplied by the electric field of that frequency. Okay, basically this is like the Fourier transform of the displacement field, D field, and this is the Fourier transform of the electric field, and they relate by this epsilon that depends on omega. And if you, when we went through the Fourier transform chapter in math physics, we up to this point we have a product of function that depends on omega. When you do to go back to the real space, or in this case the time temporal space, then that becomes what we call the convolution. Actually, it becomes an integral. Is the because you're product of this two, so it doesn't depend on the real electric field in as a function of time. They actually involve an integral of that one. So in this case, we go back to the time domain. X2. Now we jump to 7.1.11. Skip a lot of them to actually involve. I mean, in this case, Jackson separate the two terms. That doesn't matter. Like this, up to here is just vacuum. Vacuum is epsilon 0 times E, but then there's an integral. There's a function G tau. Tau. Right. So this is like the inverse Fourier. The form of that is like inverse Fourier transform, right? Because it's involved integration of time, but it's change of variables with t minus tau. And for the usual Fourier transform, and this is like a convolution of because you have two terms, right? It's like a convolution, and usually the convolution we integrate from minus infinity to infinity. But now you impose the constraint or physical requirement that supposedly your field, D field should not depend on the future values of E. This basically the assumption of causality. So whatever happens should depend on the past, not in the future. So so it only depends on T minus something positive. So you multiply by C. Infinity instead minus infinity to infinity. If it go to negative value of tau, that means D will depend on the future value of E. That's considered violation of causality. But I mean, it's an assumption because the original Maxwell equation is time symmetric. There's no causality. And you write down the Maxwell equation as well as the Newton's second law, the Newton force law, the Lorentz force law. There's no time, uh, no time error in that set of equation is symmetric in time too. But we impose the causality, and later on we'll trace the consequence of that, or actually the reason that we can impose the causality is that due to the dissipation of the system. Dissipation is due to some kind of thermodynamic itself. So in thermodynamic, we introduce a time error based on the second law of thermodynamics that break the time symmetry. So, and in that case, uh, that means we have a causality based on thermodynamics. So that's the implicit assumption here is that limit this rate of integration. And the mathematical consequence of this is quite significant, but then it needs a lot of complexity to show that. One result immediately is that this g function is related to epsilon like a Fourier transform. We rewrite it like epsilon. This is like epsilon is like a Fourier transform of something involving this g function. Although again we are separating this term out, so there's a one. It's effective the same. Putting this epsilon using this formula here, then you can show that by then taking the inverse Fourier transform, we get this equation. Okay, so basically this looks like a Fourier transform, right? Except that now you restrict your integration from 0 to infinity rather than minus infinity to infinity, right? And then there's one more consequence that is easy to to show, but we'll just write it out because you just substitute like minus omega here. That's divided by efficiency. It's effectively just like taking the complex conjugate, but with also taking complex conjugate omega. You can forget about epsilon zero because this is quantity. Basically, it's the negative argument is like taking a complex conjugate of the dielectric constant with the complex and the complex conjugate of omega also, because if we extend this to a complex plate, so the frequency can be complex. Okay, so that's also something that we see quite often, and in a particular case or in a special case that is of interest is when omega is real, then this omega complex conjugate is the same as omega. So you change the negative sign of a real frequency is basically taking the complex conjugate epsilon only, because and then change omega to its negative sign. Right. So that's a special case. All right. Then the rest is you need a lot of analysis on the complex omega plane, but we skip all that because we haven't done all these in that physics yet. But the final result is either written down in 7.119 or 7.120. 7.120 is the same as 119 by using the the symmetric property of omega. Now you consider omega real, then you can, by this relationship, you can show that the real part is even in omega, the imaginary part is odd in omega. And then you write down the 7 1 transit. I'm writing it down just to show to discuss the physical meaning of this one. So the real part of this function epsilon omega is equals to 1 plus 2 pi. And then there's a p. This is not a constant. This is not a variable. This is a meaning. This is a symbol. This is an operation. This is also called principal part. And some people will use pp or principal value. So some people use a script p. All this it's the same notation to indicate an operation on that how you do this integration, because the integral is singular. Omega prime, and take the imaginary part of epsilon and divided by omega pi square minus omega square. So basically, this principal part operation is that when you integrate that from 0 to infinity, somewhere along the line, omega prime will equal to omega, so that the denominator will be 0, so that's singular. And what you do is to skip over that. So this is integrate over along omega prime from 0 to infinity along this line, but somewhere along the line, that's the point omega. When you do the omega pi integration, you integrate up to a certain distance, delta, before you hit the singularity. And you skip the integration, and you resume the integration the same distance, delta, after the singularity, and continue to infinity. And that's important that you skip the same distance before it and after that. That's what it means by taking the principal part, basically avoiding the singularity. So if you integrate over that, then you hit the singularity, and that integral is not defined. You skip that is defined, but then afterward you take the limit of the 0. Obviously, that is only possible if this limit is not singular. Because in many cases, after you skip that, the integration, you can integrate it, but that would depend on delta. But that dependency, you can show that for delta goes to 0, actually it's finite. Okay, it's actually your finite, so it's not singular anymore. Okay, it's okay. So this is a principal part. Okay, and then the imaginary part. So there are two relations. These are called the Kramers-Kronig relation. So there are two of them. And these kind of relations show up in other field of physics also, not just in terms of dielectric constant. Because the mathematics is quite general, so in other situations you have this kind of thing. Minus p omega plus one principal part, and then the real part of epsilon multiplied divided by 0 minus 1 pi squared. Okay, now so these are the two relationships. Okay, and the idea is that the physical meaning is that you cannot have the medium that without dissipation, or which means that without imaginary part. The imaginary part of epsilon, we mentioned that before. that will give you dissipation. We showed just substituted that in the use of a K, then we have imaginary part in K that means decay. But if you have a medium that without dissipation or imaginary or epsilon is zero, so the whole thing will be zero, right? Because this is zero, and this means the real part is actually just epsilon zero, and because there's no imaginary parts of epsilon, it's exactly epsilon zero. But that's a vacuum situation, right? So for the first equation, you know that the only medium without dissipation is vacuum. You set this to zero, you only recover vacuum. Okay, and then obviously the reverse is that if epsilon is just the vacuum, this is -1. This is 1 minus 1, so that becomes zero. The imaginary part is zero. Obviously, the two just goes together. All right, so that's quite helpful because it means any medium other than vacuum will have some dissipation. It doesn't mean that all frequency has dissipation. It just means somewhere along the line you have dissipation at some frequency because this is an integral, right? So as long as it's not zeros at some range of omega, that would satisfy the fact that the epsilon is not exactly epsilon zero, because it's an integrate that at some frequency you have some observation, some dissipation. So epsilon is not, imagine epsilon is not zero at some frequency, then this would not be exactly zero, then the real part will not be exactly epsilon zero. Okay, so that's quite interesting. And yeah, more mathematical consequences. The the next section also talks about that related to that, but that's even more math. So we'll have to skip 7-11 also. But a simple example is that we can immediately do for using this integral is that if you have a imaginary of epsilon that is just exactly has a spectral line or absorption at a particular frequency, and this frequency is omega sub zero. Right? You have a, it means you have a very peak. It's like a pulse value, right? That is, right? You have imaginary part like that, like it's so mathematically you can write that as delta function. So imaginary it's like an injections term is you have some constant just for normalizing pi k over 2 omega sub zero delta. So this spike is like a delta function. Right. Now you substitute this into this integral, then it's easy to do because it's a delta function. You just substitute whatever omega pi is, change it to omega sub zero. And one more thing is that is for omega pi. Let me substitute omega pi equal omega sub zero only when because you integrate, you skip the part, you skip the value of omega pi equals omega. So if omega sub zero is exactly omega, then this integral, because of the principal part, will skip that. So the delta function will give you zero. So in that case, epsilon, real epsilon omega will be equals to epsilon zero. So the final result is that if you substitute this into that, this will equals to so for omega zero not equals to omega, you get just 1 plus put everything here. So you pi over 2, cancel this 2 over pi, and then you have k. And then change everything into this is epsilon 0. This is divided by epsilon 0. This, yeah, there should be an epsilon 0 somewhere. I can see each solution have to epsilon 0. I mean, that's not very important. Example about that. Or maybe this is maybe just has a typo somewhere. That should be if the whole thing is given by that. Then you have k. This change omega sub 0, but cancel with this omega sub 0. So everything cancel. And the only thing is omega 0 square minus omega square, which is 7.121. Oh yeah, that's Jackson 121 without dividing by epsilon. This is dividing by epsilon. So that's fine. So you actually have epsilon 0 and that's fine. This is for omega 0 not equal to omega. Okay, but 0. Actually, not 0. This is 0, but this is 1. So, okay, so so you plot that this implied space. You plot the real epsilon over epsilon 0. Then obviously that you have this is as a function of omega. Somewhere along the line is because of 0. So when omega 0 is somewhere greater than 1, because we set this to 0 with k divided by omega sub 0 square, and then goes to infinity, and then when it is smaller than, it actually becomes negative. This term becomes negative, but then go back to positive some distance later, and then goes to infinity this way. So that's the real part. This imaginary part is like that in the real part. Okay, and we saw some. This is divided by epsilon 0. So at infinity, omega goes to infinity. This is 0. So get back to okay. Right. And obviously, this is just singular, and this is unphysical because delta function is singular. So you assume a singular imaginary part. Obviously, you have the real part is singular also. But if the real imaginary part is not singular, it's just a very sharp peak, but the well-behaved function, then obviously you should go to. I mean, there's a value of 1, so then should be smoothly connecting these two. That would be something similar to what we discussed before. We have this molecular model that with some dissipation, and then we derive that this special relation. Not this, derive the epsilon for that model, and then we show that the real part is something like that, the imaginary part is something like that. When you get close to one of the intrinsic oscillatory frequency of the oscillator, then you get some behavior similar to this kind. I mean, like this model. Okay, so we get back to what we had before using this integral. Okay. So this means that this is more general than what we discussed before. What we discussed, we start with just a simple molecular model, getting some of this behavior, but this is general. This is without actually specifying what the epsilon is, but we still get similar results. Okay.